Welcome back. In the last video we have seen how a Fourier series converges when f is piecewise differentiable function, that is also called piecewise smooth function. Okay. So, this we have already proved that when f is a piecewise differentiable function, that means the derivative exists and that is piecewise continuous function, then the Fourier series converges pointwise to the function or the signal f x. When f is a continuous, only continuous function on the interval minus L by 2 to L by 2, then the Fourier series, if the Fourier series converges, if it is converges, then it has to converges to the signal function f x at each point f x, when at each point of x where f is continuous. Otherwise, it continues, it converges to the value of the jump, average value of the jump across the discontinuous point, okay, a discontinuous point x. So, if f is discontinuous at x, then if the Fourier series converges, then it has to converges to the average value f of x plus f of x minus divided by 2. So, half of that, so it is basically average value of those left side and right side value of the function at that point, discontinuous point x. So, we will see today, so just an example, we will just start with an example, and we will see how most of the functions you see, whatever function you take, elementary function with period L, which is obviously it is piecewise smooth functions. That is why you may not see a function that is only continuous but not differentiable function. It is very difficult at every point if you want. So, whatever function you take, that is mostly piecewise differentiable function. So, that is why your Fourier series always converges to the function or average value of the function at the discontinuous points. Okay. So, once you know how to compute the Fourier series, so in Mathematica or MATLAB you can actually calculate and you can plot the function in terms of this Fourier series. You consider the Fourier series and you take few terms, n terms in the Fourier series, and then you plot it, the sum of all these functions if you plot it together, it is actually converges to the function f, the signal between minus L to L, minus L to L, minus L by 2 to L by 2. So, that is the period on which it is interval on which f is defined. The thing is, but the problem with this is there is something called Gibbs phenomena. When the Fourier series does not converge to, I mean if the Fourier series converges to the average value of that function at a discontinuous point, there is something called Gibbs phenomena occurs. That means, when you compute whatever may be the number of terms in your Fourier series, you will always see that there is an error when you actually plot that sum. It is always the jumps will be, suppose the upper jump, if you look at the jump left hand side, so there may be always some overestimate or underestimate, and if it is overestimate there, so you will see the underestimate on the right side jump, that is the function value at the right side when you plot it with the n terms in your Fourier series. If it is overestimate on the left side, you will see the underestimate on the right side, or vice versa. If it is the underestimation in the left side, you will see the overestimate in the right side. That means on an average, finally you are taking the average value of it, sum of the average, sum of these functions, sum of the function value at both sides, that is f of x plus f of x minus by 2. So, one of them, so one is overestimated and the other is underestimated. So, eventually, so the error will not be there. So, finally it converges to the average value, but you cannot fix number of terms, so that you cannot fix however large the number is. There will always be an error on the left side of the curve at some in the neighborhood of a point that is where f is discontinuous, jump discontinuity. Okay. So, we will see with an example that is called Gibbs phenomena. So, before we do that, we will just do this example, we will just take the signal function over minus L by 2 to L by 2, the simple function we will consider, and we get this we get the Fourier series for that. So, what is this example is consider find the Fourier series. Find the Fourier series for the function f of x. What I consider is the simple function I consider. So, that we will establish for this function what is the what do we mean by Gibbs phenomena. Through this example we will establish the phenomena, that is called Gibbs phenomena. This is half, is actually minus L by 2 to L by 2, minus L by 2 to 0, this is 0, and this is between 0 to L by 2, this is L. So, if you consider this function minus L by 2 to L by 2, so what you have is initially you have a minus half and again you have plus half. So, what is from the theorem? So, from the theory that you learned, you clearly see that this function is smooth here, it is a differentiable function. What is the derivative here? Within this the derivative is simply 0 here, there is a constant function here, here it is 0. Okay. So, derivative is actually continuous, even this side is derivative is 0, derivative is 0. So, derivative is actually 0 everywhere inside this minus L by 2 to 0 and 0 to L by 2. At 0, if you look at the right limit and left limit of the derivative, they are also 0. So, it is a continuous function, but otherwise, so because of that the given function is piecewise differentiable function. Piecewise in fact is a continuous function. Okay. So, we will write piecewise differentiable function. So implies by the result that we have a Fourier series converges to the function f x, given function. Okay. So, what is the Fourier series? That is sigma n is from minus infinity infinity Cn cos n omega x, sorry, e power Cn e power I n omega naught x. This converges to f x. So, what does it mean? That means this one, this is equal to x for every x, wherever x is continuous. So, where is this one? So, where is the x is continuous? Minus L by 2 to 0, it is continuous. So, when x belongs to minus L by 2, so including the point 2, so here it is not. At this point the right side this value is minus half, and the left side means, so these values you have to consider here. So, that is right side. So, that is right side. So, there is a left side of, so this limit is actually the value of the function is minus half. So, this limit is minus half at this point. So, here if you look at this side, these values you can always view the values here. So, you have to go here. So, in this is a simply function value half. So, one side is function value is minus half, other side is function value is plus half. So, here the function is not continuous, the function value here and here at the end points should be same. So, they are different. So, implies a function value is not continuous at the end points. That is how you can recognize, because you look at the limit of this function, limit f of x as x goes to minus L by 2 positive side is actually minus half, clearly is a constant function here. Now, what happens to this limit f of x as x goes to minus L by 2 minus negative side, that means this side. These values are same because it is periodic, they are here. Why is it periodic? You can always extend as a periodic function, you can go on like this. So, again you can go down and up like that. So, values here are exactly values here. So, if you view here they are like this. So, these values are same as values here. Okay. So, that is the reason. So, values on the left side are same as values here. So, if you view this one, this is same as the limit f x as x goes to minus L by 2 plus L by 2, L by 2 negative. So, this is same as half. So, you see that the value one side is plus half, other side is minus half. So, implies it is a discontinuous function at the end point. So, where are the points it is continuous? It is only in the open intervals, this union 0 open interval L by 2, okay, from the result. So, we will calculate what this is. So, what are your CNs? CNs are simply 1 by L integral minus L by 2 to L by 2 f x e power minus I n w naught x. What is your w naught? W naught is 2 pi by L dx. So, these are your coefficients, Fourier coefficients. So, if you calculate 1 by L, so you can write this minus L by 2 to 0, f x is minus L by 2 to 0, it is minus half. So, this is minus half e power minus I n omega naught x dx plus 0 to half, 0 to L by 2, it is plus half, half e power minus I n omega naught x dx. So, I just split this integral into two parts. So, what you get is 1 by L minus 1 by L, and this becomes e power minus I n omega naught x divided by I n omega naught, that is the antiderivative, minus L by 2 to 0, and this is minus minus plus. So, you again you have minus I, and you bring this I comes up, it becomes minus I, because I square equal to 1. So, this implies I times I equal to minus 1. So, this is minus 1. So, I equal to minus 1 by I, or minus I is 1 by I. So, this is from complex variables, I is square root of minus 1. So, I means imaginary number, that is square root of minus 1. So, this one plus, again because of here it is minus, for the other integral 1 by 2 L. So, there is a 2 missing here. So, half, that is half here, 1 by 2 L, and you have here I n omega naught into e power minus I n omega naught x, and if you bring this up, it is going to be plus I, and again for this 0 to L by 2, that is the limits you have to apply. So, what you get is 0 is minus I by 2 L. If you take it out, what you have is 1 by n omega m w naught minus e power minus I n omega naught L by 2 divided by n omega naught plus e power. Now, here this is for the first term, the second term is I by 2 L, what you get is e power minus I n omega naught L by 2, and this is, I think, is going to be minus minus plus. When you put x equal to this is going to be plus, and this term have L by 2 by n omega naught minus 1 by n omega naught. So, you get minus I by 2 L n omega naught, and here also minus 2 I by 2 L n omega naught plus I by 2 L, right, I by 2 L e power I by 2 L n omega naught, and this is this e power I n omega naught L by 2 into plus e power minus I n omega naught L by 2. So, that will give me 2 cos. So, 2 goes here, this is going to be cos n omega naught L by 2, that is what is the result. So, this is equal to minus 2. So, 2 I. So, we have I by L n omega naught plus I by L n omega naught cos n omega naught L by 2. So, where is this? These are all Cn's. N is running from, if I put n equal to 0, there is a trouble here. So, n equal to 0 I cannot, because it is 1 by n. This is undefined term. So, is n Cn infinity. So, when n equal to 0, you have to integrate separately by putting n equal to 0 this integration. This is valid only for n is plus or minus 1, plus or minus 2, and so on. Okay. So, finally, this is actually equal to I by, so omega naught is 2 pi by L. So, 2 pi n, L omega naught is 2 pi n, and you have a minus 1 plus cos 2 pi n, cos 2 n pi is minus 1 power n. Okay. So, I by L n w is I divided by 2 pi n. So, cos n omega naught L by 2 is cos 2 n pi, cos what is that one, 2 pi by L, L goes, 2 goes. So, cos n pi is minus 1 power n. Okay. So, this is what you get for n is from plus or minus 1, plus or minus 2, and so on. So, if you see this is actually equal to 0, 0 if n is even, then minus I by pi n if n is odd. Is this true? So, if n is odd, n equal to 1 or minus 1, and what you see is it is going to be minus 2 goes to minus I by pi n. Okay. This is what you have. So, and this is only, and n is non-zero. This is 2 pi by n, right? Yeah, that is fine. So, this is what you get. This is your Cn, and which is n is not equal to 0, but we need C0 also. C0 is actually 1 by L integral minus L by 2 to L by 2 f of x e power minus I n omega naught x. When n equal to 0, that is 1, you have dx. This is your Cx, this is your C0. So, 1 by L, and what you get is minus half minus L by 2 to 0 f x, that is minus half dx plus half 0 to L by 2 dx. What you get is 1 by L. So, this is going to be minus half minus 1 by 2 L, and this is going to be 0 minus L by 2. So, that is L by 2 plus 1 by 2 L by 2. So, this is going to be, this is actually 0. So, C0 is 0 and Cn is this. Cn is actually 0 if n is even. If n is odd, it is actually value is this. So, this implies your Fourier series is Fourier series for the given function sigma C n e power minus I n plus 1, right. So, I n omega naught x, n is running from minus infinity to infinity. This is equal to, you have sigma, n is from minus infinity to infinity and n is not equal to 0, because n equal to 0 it is anyway 0, and what you have is odd. When n is odd, odd means you can and n is odd, only for odd you have minus I by pi n into e power I n omega naught x. So, you have this n is from minus infinity to infinity, n is not equal to 0 and n is odd. So, what is this one? This is actually equal to, so you can write minus I divided by pi times, if n is odd, so you can say 2n minus 1, n is running from 1, 2, 3 onwards, okay. N is odd means that, n is odd means is equivalent to n equal to 2k minus 1, k is running from, and n is not equal to 0, means they are equivalent to this. So, you have k is running from 1 to infinity, okay. In fact, minus infinity to infinity, plus or minus 1, right, plus or minus 1, plus or minus 2 and so on. This is what is still odd both sides. So, you have 2k minus 1 e power I n is 2k minus 1 w naught x, w naught is 2 pi by L. So, w naught x, this is equal to k is from, so k, I just remove k, so you get is n is minus infinity infinity, I use the index n, and this is cos, that is see given function f is a Fourier series is this, and this has to be equal to f x wherever it is continuous. So, I write this here. So, f x is this, so this implies f x is this, f x is, so where is this valid? X belongs to minus L by 2 to 0 union 0 to L by 2. So, in this open interval it is true. So, what you get is f x. Now, f x, if you look at this left hand side, f x is a real valued function. So, right hand side you should take only a real part, imaginary part has to be 0, okay. So, all together, so that also you will have an extra result. So, what you have is, if you just separately this complex number, if you write real part and imaginary part separately, what is the imaginary part is minus I, and what you get is cos 2k 2n, I am writing in terms of n, 2n minus 1 omega naught x divided by pi times, so pi anyway constant goes out, 2n minus 1. So, this is the imaginary part plus a real part is I square minus 1 minus minus plus, what you are left with is n is from minus infinity to infinity 1 over pi times 2n minus 1, you have sine 2n minus 1 omega naught x, that is what it is, okay. So, this has to be equal to the real part, which is this. So, this implies given function f x, that is given function f x, which is minus half and plus half in those intervals, is actually equal to, n is from minus infinity to infinity 1 over pi is constant, sine function 2n minus 1 w naught x, that is 2 pi by L x divided by, this is the whole sine thing, you have to, this is the sine of whole thing. So, into divided by 2n minus 1 is this, and what is left? What is left is this one. So, that has to be 0. So, this is what you get, a new identity, that is may be the fact, divided by, it has to be true, this is equal to 0. This we do not care what it is, but that value is actually 0. You get an identity, the fact that the sum of all these things are 0. And what you get is this is your Fourier series that converges to the point. We can do something else here. So, what we do is instead of this, so what you get is you can rewrite, because it's a Fourier series is converges in this, we can always rewrite, this is minus I by pi is sigma, k is from, and of course k is not equal to 0. So, that is what is thing, and if I do not use k, n is from 1 to infinity, and what you get is 1 by 2 n minus 1 e power I 2 n minus 1 w naught x plus, so if I add here, so this is going to be n is from minus 1 to minus infinity to minus 1, again 1 by 2 n minus 1 e power I 2 n minus 1. I just split it into two parts. So, from minus I by pi, so let us not rewrite, we do the same thing. So, this implies f x equal to, this is running from k is from minus infinity to infinity, and k is not equal to 0, and you get minus I by pi by 2 k minus 1, this is going to be e power I just leave it like this. So, e powers, if you rewrite, put this instead of k, you write it as n as an index, n is not equal to 0, and n is running from minus infinity to infinity, integers, minus I over this, and e power I 2 n minus 1 w naught x. This is valid in this interval. So, this will give you your because f left hand side, the given function is a real valued function, a real value has to be equal to right side the real value, whatever the remaining imaginary part, that has to be 0. So, you have to equate, you can equate both sides, real and imaginary parts. So, here left hand side real part is itself f, and if you take the real part here, that is going to be sigma n is from minus infinity to infinity, n is not equal to 0, and what you get is 1 by pi sin I sin n 2 n minus 1 w naught x divided by 2 n minus 1. So, that my I and minus I becomes plus. So, this is what you get the Fourier series for f, and that is happen to be sine series, which is valid here. Union the open interval, this one. So, what happens, there is another part, that is imaginary part, that imaginary part, if you equate, a real part you equated, now you equate the imaginary part here in this equality, what you get is 0 equal to sigma n is from minus infinity to infinity, and n is not equal to 0, and what is the imaginary part is minus 1 by pi 1 by 2 n minus 1, and this is cos 2 n minus 1 w naught x, where w naught is 2 pi by L. So, for every x in this interval minus L by 2 to 0 union 0 to L by 2, this quantity is actually 0. So, minus pi is constant. So, this has this overall, this quantity has to be 0. This is the equality you will get because of as a byproduct from the Fourier series. Okay. This is anyway we do not use this is immaterial. So, what we require is this is your Fourier series for the given function, that is piecewise continuous function, piecewise smooth function, piecewise differentiable function, which is like this minus half and plus half here. This is valid only because this value here and value here they are not same, is also discontinuous point. This end points are also discontinuous points. Another point is 0 is the discontinuous point. So, you have 3 discontinuous points at which what happens. So, what happens at 0? First consider at x equal to 0. At x equal to 0, what we see f of 0 is f of 0 plus is half, f of 0 minus is minus half. So, the average value is simply half, f of 0 plus f of 0 minus divided by 2 is half plus half divided by 2, that is half. And what we have seen already that this Fourier series, which is 1 by pi times sigma n is from minus infinity to infinity, n is not equal to 0, sine 2n minus 1 w naught x divided by 2n minus 1. This, if you take x equal to 0, this is equal to half when x equal to 0, x equal to 0. So, average value at 0. So, what is this one? Average value of this is half and this is minus half, that is what we made a mistake. So, here is minus half, when you add this is going to be half minus half divided by 2, which is 0. So, clearly the average value has to be 0. So, when you put x equal to 0, so obviously this Fourier series which is also 0, which is true. Now, what happens at x equal to minus L by 2 or plus L by 2, both places what happens, because their function is the discontinuous function, you calculate f minus L by 2 and plus this plus side is same as is actually equal to minus half, and f at minus L by 2 actually you need plus L by 2 minus side. At the end points you need, right, at every end point what happens, the Fourier series converges to f L by 2 plus f minus L by 2. So, you just calculate minus L by 2 and minus L by 2. So, these are values which is half. So, again f of minus L by 2 plus f of L by 2 divided by 2 is again 0, because they are minus half plus half. And this value again they are, this is half and this is minus half, average value is 0. So, here also it is 0, which you can easily see here. So, 1 by pi, if you put here x equal to minus r plus or half plus half, what you end up is 1 by pi, n is from minus infinity to infinity, n is not equal to 0, sine 2n minus 1 w naught plus or minus half. You put plus or minus half as x, what happens to this, and x equal to plus or minus half, any one of them if you put L by 2 plus or minus L by 2 at both the end points, the value has to be 0 from the theory. Is it really true? So, if you look at term sine 2n minus 1 2 pi by L x equal to plus or minus L by 2. So, that comes plus or minus because of sine, it comes out of sine. So, 2 goes and pi times this, which is 0, we know that this is true, and n never be 0. So, that is why each term for every n non-zero or whatever, when n is non-zero, n is running from minus infinity, the denominator never 0 and numerator is 0. So, because w not equal to 2 pi by L, so this is 0. So, it is verified. So, this is how you see that the Fourier series converges a point to the function at a continuous point when the function is continuous at that point, otherwise its average value, it converges to the average value. That is what we can see from this example. So, what is that I am trying to say from for this function? We will use it, we will demonstrate what is the Gibbs phenomena, we will just try to explain, and I will remark on convergence of some other thing. So, Gibbs phenomena is, we will try to see this with some other example in the next video. Gibbs, yeah. Gibbs phenomena, what you are trying to see is you have this is your function, which is this is your x axis, this is your L by 2, this is your 0, and this is your minus L by 2. Okay, this is your minus half and this is your plus half, which is constant function. Okay. Now I try to take in this Fourier series, what is your Fourier series? 1 by pi sigma n is from minus infinity to infinity, n is not equal to. So, this is your Fourier series. In this I fix my n, w naught x by 2n minus 1. I fix my n. I take some n terms, let us say some 10 terms, 5 terms, 10 terms, any number, okay, 1000 terms and so on. You can take anything. When you do, what you see is that eventually as n becomes bigger and bigger, this Fourier series is actually converges. So, you see when you do this one, this is converging, but the problem here is you will see that there is an error here. See that it is actually underestimated. This is less than, more value, less value is actually the underestimation of half. What is the underestimation of half is? Overestimation means more than, more value, underestimation means it comes down. So, here it underestimated, overestimated, okay. So, it is overestimated here. So, it will, what happens in this here, it will underestimate, this side it will underestimate. So, you will see that this kind of plot. So, the value, the limit value is here and the limit value is here lower. So, the jump is same, okay. Actual value is this value and this value, plus or minus half and plus half, the difference is so average value is 0, but here average value. So, what happens here? So, when it underestimates, half plus half minus some epsilon, here half minus epsilon. So, this amount, if it is underestimated, that means it is added minus epsilon. If it is overestimated like this, and here it is underestimated, okay. So, it is something like this. I can show you by plotting it. Everything is converging here, but here it starts, there is error will be more, here is less, and then it goes here and here it is more. Sorry, this should go, and here is fine, and there is small errors, and then it is more here. So, if it is less here and this is more here. So, if it is less here, this will be more here at this point, the limiting values. So, whatever may be, this is plus or minus will be added or subtracted, finally a jump, that is this value would be same. So, this value, finally the convergence value is same, but whatever may be n big, any number of terms you take in this Fourier series, you will not be able to capture the actual image of the function, that is actual value. So, that is the step function, you will never be able to cover it with your these functions by choosing any number of terms, okay. So, even if you choose a big number, there will always be some error here. So, more error here, I mean if it is lesser than this value, you get more value here. So, on an average, a Fourier series actually converges to the average value of it, which is actually same. If it comes down here, and it will go down here, if it goes up here, this will go up here, the error. So, that is called a Gibbs phenomena. We will explain this with an example maybe in the next video, and explain what is Gibbs phenomena through that example. Thank you very much.